Okay, so welcome back to this next video in which we are discussing the Sylow theorems. Okay, so we're currently in the process of proving the second Sylow theorem. Okay, and we've discussed that to do this, we are studying this group action by the group capital G on this set capital S, where this set capital S is the set of all left cosets of the Sylow P subgroup capital H. Okay, right. So we've said that this group action is transitive on the set capital S, so there's only one orbit, okay? If you have any left coset A bar in this set capital S, you can send it onto any other left coset in this set capital S by picking some element of the group cleverly to act on that left coset A bar. Okay, right. Now what we're discussing is the stabilizers of a left coset in this set capital S in the group capital G. Okay, right, so we've discussed that the stabilizer of an element A bar in the group capital G will be the subgroup of the group capital G, which is all elements of the group which, when they act on A bar, gives A bar back again. Okay, but now let's apply the definition of what it means for an element of the group to actually act on a left coset and gain some more insight into the condition on these elements of the group that are going to be in the stabilizer of a left coset A bar in the group G. Okay, so just applying the definition then, this becomes all elements of the group such that when I use little g to left multiply any element of the left coset of the subgroup capital H under the element little a, I get another element of that left coset of the subgroup capital H under the element little a back again. Okay, so it needs to be the case that little g composed with some element of this left coset of the subgroup capital H under the element little a, so something of the form AH, like so, is going to equal another element of this left coset of capital H under the element little a. Okay, so it's going to equal some AH prime. Okay, so it must be the case for all little h is an element of capital H that there exists an H prime which is an element of capital H, such that this is true basically, that when little g composes with this element, it gives me some other element of the same left coset basically. That's what needs to be true. Okay, now what we can do here is just rearrange that condition, okay, to get an actual explicit formula for little g. Okay, so what I can now do is rearrange this like so. I can say, okay, let's compose with h's inverse on the right on both sides of this equation, and what we'll get is GA, because the h will cancel with h inverse on the left side of this equation, is equal to AH prime, and then we'll have h inverse here. Okay, and then what I can do is compose on the right hand side of both sides of the equation with A inverse, and then I'll get that G is equal to AH prime H inverse A inverse. Okay, now that's very interesting, and this is indeed where the concept of the conjugate of the Sylow P subgroup capital H under some element of the group is actually going to come from, because what does that tell us about little g? Okay, this portion in the middle, h prime times h inverse, that is just some other element of the subgroup capital H, so we might as well call it capital H bar. So we've just got some element of the subgroup little h bar here in the middle, and we've conjugated it by this element little a, so we could write this as AH bar A inverse. So what that's telling us is that all elements that are in the stabilizer of the left coset A bar in the group capital G are actually going to be of the form some element of the Sylow P subgroup capital H conjugated by this element little a basically. That's what that is telling us. What I now want to show you is that actually the stabilizer of this element A bar from the set S is actually going to be equal to the conjugate of the subgroup capital H under the element A. Okay, so remember this is the subgroup as we know it will in fact be, of all things of the form AHA inverse, where H is any element of the subgroup capital H. Okay, so you go through all elements of the subgroup capital H, you conjugate them all by this element little a, you stick them all into a subset together, and that's what we mean by the conjugate of this subgroup capital H under the element little a. Okay, and we know that that will in fact be a subgroup of the group capital G, and it will, as we've discussed, be another Sylow P subgroup of the group capital G, and this is where this concept of conjugating the Sylow P subgroup by another element of the group is actually going to come from, and we know that it appears in the second Sylow theorem. Okay, right. So what I want to show you then is that any element of this conjugate of the Sylow P subgroup under the element little a is actually going to stabilize the left coset A bar. Okay, what I've shown you so far is that all things in the stabilizer of A bar in the group G are going to be of this form. I haven't shown you that anything of this form is actually going to stabilize the left coset A bar. Okay, right, so let's now show that. So let's show that if I have any element AHA inverse, and I use this to act on this left coset of the subgroup capital H, A bar, that I will get the left coset A bar back again. So this is what I want to show now. Okay, right, so let's do so. So what we're going to do then is we're going to use this element to left multiply all the elements of this left coset of the subgroup capital H under the element little a by, basically. So this new subset that we will end up with will be all things of the form AHA inverse composed with AH, where H is an element of the subgroup capital H. Okay, so this portion here is all elements of the left coset of the subgroup capital H under the element little a. Okay, now all we're doing is left multiplying them all by this element AHA inverse. Okay, now of course what's going to happen here, and I should say, there's a problem here. I should change the notation. Let's make that an H bar here. Okay, so this little h here was some fixed little h that we'd chosen from the subgroup capital H, okay? Whereas this one is the one that varies for the purposes of this set. Okay, so those shouldn't have been notated by the same thing, so I've just corrected that now. Okay, so the brilliant thing here then is that A inverse will compose with A to give the identity element here, and what we'll end up with is something of the form AH composed with H bar, where H bar is allowed to vary over any element of the subgroup capital H. Okay, so now what we've got is this constant little h, which is some element of the subgroup capital H, now multiplied on the right by all elements of the subgroup capital H. Okay, so effectively we are constructing the left coset of the subgroup capital H by this element little h. We're allowing little h bar to vary over all elements of the subgroup capital H. We're then left multiplying them by little h, and we know that the answer to that will just equal the entire subgroup capital H. So in fact, little h composed with little h bar will vary over all elements of the group capital H, if we're allowing little h bar to vary over all elements of the subgroup capital H. So we could replace this, if you like, with an h double bar, a little h double bar, and we could say that this is equal to the set of all things of the form little a composed with little h double bar, where little h double bar is allowed to vary over all elements of the subgroup capital H. And that is, of course, the definition of the left coset of the subgroup capital H under the element little a. Okay, so what that then shows us is that anything of this form, any element of the subgroup capital H conjugated by the element little a, will in fact be a stabilizer of the left coset of capital H under the element little a. So in fact, this stabilizer of this left coset A bar is in fact going to equal the Sylow P subgroup capital H conjugated by little a, and that's where the concept of conjugating the Sylow P subgroup by an element of the group is actually going to come from, and why it appears in the statement of the second Sylow theorem. Okay, right. So that now is all of the setup that we need. Now we are ready to actually prove the second Sylow theorem. Okay, right, so let me just get the second Sylow theorem back up and we'll see what we need to do. Okay, so here then is the statement of the second Sylow theorem, that if we have a subgroup capital K such that the prime p divides the order of k, so the order of k is some p beta times m bar, where m bar is some portion of m from the order of the entire group. Okay, it must be the case that there exists some conjugate of the Sylow P subgroup capital H, such that when we intersect it with this subgroup capital K, what we end up with, this new subgroup, is going to actually be a subgroup of capital K because it's completely contained within capital K, and it's in fact going to be a Sylow P subgroup of capital K. So its order is going to be p to the power of beta. So that's what we now want to prove. Okay, right, so the way we're going to do this is we're going to say, okay, let's now use this subgroup capital K. So let K be a subgroup of capital G such that P divides the order of capital K. Okay, so there is some power of P in the order of capital K. And I think a nicer way of saying this is once again to write explicitly out that the order of this subgroup capital K is in fact going to be P to the power of beta times some m bar, okay, where beta is between 1 and alpha, and that m bar is some portion of m. Okay, right. So what we're now going to prove then is that we can find that conjugate of the Sylow P subgroup capital H, which if we intersect it with capital K is going to be a Sylow P subgroup of capital K, so it's going to have order p to the power of beta. Okay, so how are we going to do this then? Well, what we're going to do is we're going to use the group action that we have just been investigating so intently. Okay, and we're going to restrict that group action down to the subgroup capital K. So we're going to use this group action, which was previously a group action by the entire group capital G on the set capital S, which remember was the set of all left cosets of our subgroup capital H, okay, in the group capital G. What we're now going to do is we're going to restrict this down, and let me draw a picture of this. We're going to form a very much so related group action, but it's going to be a group action by the subgroup capital K on the set capital S. Okay, so let me show you how this is going to work. So once again we'll have our group action composition table here, and this time in the row portion here we will only have all the elements of the subgroup capital K. So rather than having all the elements of the group capital G, we will now just have all the elements of this subgroup capital K. So we have decreased the number of rows we have down to just this subgroup of the group capital K rather than the entire group. Okay, we won't, however, have decreased the column portion. The column portion will have remained exactly the same. Okay, we'll still have all elements of this set, capital S, up here. So all left cosets of that Sylow P subgroup capital H in the group capital G are still up there. And the entries in the composition table are going to be exactly the same, basically. Okay, so all the elements of this subgroup capital K will have been elements of the group capital G. Okay, so what they are acting on an element of the set capital S is going to be exactly the same. Okay, so some little k acting on a left coset A bar is still going to equal the left coset that contains the element K composed with A, basically. So the entries in this restricted portion are just going to be exactly the same as they were in the larger group action composition table. Okay, and this restricted group action composition table is still going to obey the axioms of group actions, basically. Okay, and the reason is that we really just haven't changed it, we've just cut a bit off. Okay, so axiom number 1 of the group action, that's still going to work for all elements of my subgroup capital K. Okay, if it worked for the entire group capital G, then it's still going to work for this subgroup of capital G, which is capital K. In addition, axiom number 2, the one concerning the identity, well, the row for the identity is still exactly going to be there. It's still going to be exactly the same. Okay, so that's still going to be true as well. So indeed, this is still going to be a valid group action, but now it's a group action of the subgroup capital K on this set capital S rather than the entire group on the set capital S. Okay, right. So what's now going to be interesting is that this group action of the subgroup capital K on the set capital S might not actually be transitive anymore. It might not be the case that this only has one orbit anymore. Okay, you might not be able to send any left coset of the subgroup capital H onto any other left coset. Okay, so now what we can do is we can partition up the set capital S into the orbits of this new group action of the subgroup capital K on the set capital S. Okay, so let me draw a picture for this then. So here we have our set capital S once again, and previously there was only one orbit when we were acting the entire group on capital S, but now it might be the case that there are more than one orbit. I mean, it might still be the case that the subgroup capital K still is transitive, acts transitively on the set capital S, but it might not be the case. Okay, so now we might actually have capital S being partitioned up into some orbits, and we know that will be a well-defined partition. Okay, but now what this allows us to do is say that the order of this set capital S, which previously we worked out as being M, that portion from the order of the group after we've pulled out p to the power of alpha, this is going to be equal to the sum of the orders of all of these orbits. Okay, so what you can do is sum up the orders of every single one of these orbits, okay, and that will have to equal the order of the entire set. Okay, so that's basically just saying that the order of the entire set is just the sum of the orders of all of these subsets that overall make up the entire set. Okay, now, what we're actually going to do now is apply a very similar argument to what we saw in the case of the first Sylow theorem. Okay, what we know is that P, this prime P, does not divide the order of the set capital S. Okay, and the reason we know that is that the order of the set capital S is this M, and M had every single possible power of P pulled out of it already. Remember, the order of the entire group was equal to P to the power of alpha times M. We had pulled every single power of P we could out, and M was what was left over. So P does not divide M. P does not divide the order of S. Okay, the order of S is not a multiple of P. Now, what does that once again mean? And this is how I say it's a very similar argument to what we did in the case of the first Sylow theorem. Okay, it means that there must exist an orbit in this set capital S which has order that is not a multiple of P. Okay, because if all of these orbits had orders which were multiples of P, then when you add together loads of things which are multiples of P, you end up with something that's a multiple of P. So it would imply that the order of S was a multiple of P. So at least one of these orbits here that we've partitioned the set capital S up into must have an order that is not a multiple of P, basically. Okay, so arbitrarily, let's say that it's the orbit of some left coset, which once again we'll call A bar. Okay, so let's say that this orbit containing the element A bar, which will be all of the left cosets that A bar can be sent onto by elements of the subgroup capital K acting on it. Okay, let's say that it has an order which is not a multiple of P. Okay, so this is the new important equation that we have, that P does not divide the order of this orbit of this left coset A bar here. Okay, and we can always find such an orbit for which this is true. Okay, that's my argument here, that you will always be able to find an orbit. If you look hard enough, there's always going to be at least one there. Now, if this group action by the subgroup capital K on the set capital S was indeed transitive, then of course the orbit will be the entire set capital S, and of course then that orbit, the order of that, will not will not be a multiple of P, because we know that the order of the set S is not a multiple of P. Okay, right, but you can absolutely always find some orbit of this set capital S which is not a multiple of P, so P does not divide it. Okay, right, now what we're going to do is use this to construct, to arrive at the second Sylow theorem. Okay, so what we're now going to do is apply the orbit stabilizer theorem. Specifically, we're going to apply the finite form of the orbit stabilizer theorem. Okay, so remember, the orbit stabilizer theorem says that the order of the orbit of the element A bar in the set capital S must be equal to the number of left cosets of the stabilizer of this element A bar in the group capital K, in the group capital K. Okay, so it must equal the index, but we know that the index in the case of finite group theory is just going to be the order of the group capital K, and remember, the order of the group is now the order of capital K, because the group that we're using in this group action is the subgroup capital K, okay, not the entire group capital G. Okay, so it's the order of K there, divided by the order of the stabilizer of A bar, now in the subgroup capital K rather than in the entire group capital G. Okay, so this is just the orbit stabilizer theorem, which we've made use of a lot in this video. Okay, and now what we can do is quite simply rewrite this as the order of the orbit of this element A bar times the orbit, the order of the stabilizer of A bar in K is going to equal the order of the entire subgroup capital K. Okay, so where are we going to go next with this? Okay, well, next what we're going to consider is what actually is the stabilizer of the left coset A bar in the subgroup K. Well, what we have seen is that the stabilizer of A bar in the group capital G was just equal to the conjugate of the Sylow P subgroup capital H under the element A. But now what we want is the stabilizer of A bar in the subgroup capital K. Okay, so what's that going to be equal to? Well, firstly, let me just remind you of the definition of this. Okay, so this is going to be all elements of the subgroup capital K such that when they act, all little k is an element of capital K such that when little k acts on the left coset A bar, it gives you back little A bar. Okay, so all the elements of the subgroup capital K that have no effect on this left coset A bar, basically. Okay, now, we know that all the elements in this conjugate of the Sylow P subgroup by the element little a have absolutely no effect on A bar. Okay, but we don't know that they're all in the subgroup capital K. However, all of these elements in capital K which do this are going to be in here, because remember, the group action was just the restricted group action from the entire group acting on the set capital S. Okay, so any element that's in here will indeed be in here, and in fact any element that is in here and which is in the subgroup capital K will be in here, will still stabilize A bar when it's in capital K, okay, because of the way that the group action is just the reduced or restricted group action from before down to the subgroup capital K. Okay, so in fact the stabilizer of A bar in the subgroup capital K is just going to be the intersection of the stabilizer of A bar in the group capital G, okay, which is the conjugate of capital H, the Sylow P subgroup under the element little a, intersect K. So all you need to do is ask what elements of this which stabilize the coset A bar in when we had the group action by the group on the set S, okay, are it also in our subgroup capital K? Okay, well, all of those are now going to be the stabilizer of this coset A bar in the subgroup capital K. Okay, so that then is going to be what the stabilizer of A bar in the subgroup capital K is actually going to be equal to with our restricted group action. And that is why this concept of taking the conjugate of the Sylow P subgroup by some element of the group and intersecting it with this subgroup capital K shows up at all in the second Sylow theorem. That's why it's going to be important. Okay, so what we can now do is take this subgroup, and note it is a subgroup, okay, because when we intersect one subgroup with another subgroup, we end up with a third subgroup. So let me just draw a picture actually for this. So what we have now is here is the entire group, okay? So here's our entire group, and I'll just colour this in orange here. Then what we originally had is our Sylow P subgroup capital H here, okay? So here is our Sylow P subgroup capital H, okay? Then we had our subgroup capital K here. So here is our subgroup capital K, which I'll have in red here, okay? And then what we've done now is we've conjugated our subgroup capital H by some element little a, okay, which is the little a whose coset we have here. Okay, and this, remember, was the coset contained within this orbit in S that had an order that was not a multiple of P. Okay, so we've taken this conjugate of our Sylow P subgroup, AHA inverse here, and I'll colour that in vivid purple, and we've now taken the intersection of this subgroup, which we know is another Sylow P subgroup, with K, and we've got this portion here, which I'll shade in black. Okay, and that is going to be a subgroup of our entire group capital G, but more importantly, it's going to be a subgroup of our subgroup capital K, because it's completely contained within capital K, and it's actually also going to be a subgroup of our subgroup AHA inverse here, the conjugate of the Sylow P subgroup capital H under the element little a, and both of those facts are going to be important in a moment. Okay, so now just stick this into the orbit stabilizer theorem, and we've got that the order of the orbit of A bar times the order of this massive great subgroup here, AHA inverse intersect K, must equal the order of our subgroup capital K, but let's just replace that with what it's equal to, p to the power of beta times m bar. Okay, and remember, beta is between 1 and alpha. Okay, so it's less than or equal to alpha, but greater than or equal to 1. Okay, right. Now what we're going to do is use the fact that we chose the orbit here very carefully. Okay, we chose this orbit so that P did not divide the order of the orbit. This orbit was chosen because it was a special orbit, and it was the orbit that had an order that was not a multiple of P. Okay, so no power of P is in here. That must mean that this entire power of P that we've got over here must be in AHA inverse intersect K. Okay, and what I claim is that actually AHA inverse intersect K, the order of that is just P to the power of beta. It doesn't contain any part of m bar here. Okay, now why can I claim that? Well, I'm going to use the fact that AHA inverse is this group here which contains AHA inverse intersect K. Look at the picture here. AHA inverse intersect K is in fact a subgroup of AHA inverse. Okay, it's certainly a subset here of AHA inverse because it has to be contained within AHA inverse just by the definition of an intersection here. Okay, and because AHA inverse intersect K is a subgroup in the entire group, then it's also going to be a subgroup in our group AHA inverse, which completely contains it. Okay, right, so now what we can do is apply Lagrange's theorem here, which says that the order of this subgroup must divide the order of the group here. The order of this group is p to the power of alpha because it's a Sylow P subgroup of the group capital G. Okay, so that means that the order of AHA inverse intersect K can only be a power of P, i.e. it can't contain part of this m bar which is not a power of P. Okay, so it must just be this p to the power of beta. So now what I have proven then is that the order of AHA inverse intersect K must equal p to the power of beta. Okay, but here's the final line. AH A inverse intersect K, not only was it a subgroup of AH A inverse, but it was also a subgroup of capital K. So AH A inverse intersect K was a subgroup of capital K. Okay, again, just look at the picture here. It's a subset of capital K. It's a subgroup in capital G, so it's also going to be a subgroup in capital K. Okay, what we now have is that this is a subgroup of capital K and that its order is p to the power of beta, which is the highest power of p that appears in the prime factorization of the order of K. Okay, so that therefore satisfies the definition of being a Sylow P subgroup of this subgroup capital K. So it is now an element of the Sylow P subgroups of our subgroup capital K. Okay, and that then is the second Sylow theorem proven. Okay, we have proven that if you give me some subgroup capital K of the group capital G, I can always find you a conjugate of the Sylow P subgroup capital H, such that when you intersect that conjugate with the subgroup capital K, it will be a Sylow P subgroup of that subgroup capital K. Okay, so I'll have a break there, and in the next video we'll prove the third Sylow theorem.